Graphene boasts excellent thermal and electrical conductivity, but those properties belong to a single microscopic layer of carbon. When millions of these flakes are clumped together in a random, chaotic pile, they behave like ordinary carbon soot. To harness its two-dimensional properties at a macroscopic scale, those flakes need to be strictly organized. Every single atom-thick sheet must lay perfectly flat, parallel to all the others. In this breakdown, we are going to create a liquid suspension of graphene and force it into a highly ordered planar alignment. And rather than relying on a multi-million-dollar laboratory electromagnet to do this, we will use a DIY setup built from rotating neodymium magnets. By mastering this precise magnetic alignment technique, we can translate microscopic carbon properties into macroscopic metamaterials. Step 1 is acquiring the raw material. We need to extract individual atomic layers from a bulk block of natural graphite. While bottom-up methods like chemical vapor deposition can grow high-quality graphene atom by atom, they require extreme heat and are incredibly difficult to scale up to the volume we need for a macro composite. Instead, we use a scalable top-down approach called liquid phase exfoliation. By applying ultrasonic shear forces to graphite submerged in a liquid solvent, we can mechanically peel the one-atom-thick sheets apart. You have to be careful with the sonication process here. If the mechanical forces are uneven or the solvent ratio is off, the flakes will rapidly aggregate back together and settle uselessly at the bottom of the vial. But when executed properly, this top-down exfoliation provides our starting point, a stable liquid suspension of independent two-dimensional flakes ready to be manipulated. With our suspension ready, the most intuitive next step is to place a standard static neodymium magnet right next to the vial to pull the flakes into a perfectly uniform horizontal direction. This time-lapse sequence shows exactly what happens under that static field. Between 0 and 10 seconds, the micro-sized flakes react, but instead of laying flat, they turn and stand completely vertical on their edges. This behavior is driven by a physical property called Landau diamagnetism. Graphene's free-flowing pi electrons generate an opposing magnetic field. To minimize repulsive energy, the flake rotates its narrowest edge toward the magnet. This creates a strict limitation. The static magnet locks one axis, leaving the flake entirely free to spin on its edge like a coin. A single static magnet cannot create a true two-dimensional plane. We have to find a way to eliminate that final rotational degree of freedom. The solution requires a hardware upgrade, a motorized rotary base equipped with two separate neodymium magnets. This diagram shows the exact layout. Two magnets face each other with alternating poles, leaving a central gap for the cuvette on the rotation axis. As the motor spins, it creates a rotating horizontal magnetic field, pushing flakes from every horizontal direction sequentially. Because the field is alternating and repeating in that horizontal plane, it constantly corrects the flake's orientation. The spinning motion strips away that final degree of freedom, forcing every single sheet to lay perfectly flat and parallel to the desk. To make this work, there is a strict operational threshold. The motor must spin at a minimum frequency of 5 revolutions per second. If you rotate the magnets too slowly, the flakes have enough time to drift and lose their orientation before the field completes its next rotation. By shifting from a static magnetic field to a dynamic, rotating one, we trick the chaotic flakes into a tightly locked macroscopic planar formation. The flakes are microscopic, so we cannot verify this alignment with the naked eye. We have to use cross-polarized light filters to prove it worked. Notice the contrast in these reference images. The unaligned suspension in panel A is completely dark. In panel C, under the rotating field, the cuvette glows. This is birefringence. The perfectly flat parallel sheets act like a crystal, letting polarized light pass straight through. And this chart confirms the data quantitatively. The order parameter curve for the rotating magnetic field approaches a near-perfect alignment score of 1.0, completely outpacing the low alignment achieved by the static field. To make this alignment permanent, we go back to the beginning and replace the standard liquid solvent with a UV-curable polymer resin. While the motor is actively spinning at 5 revolutions per second and holding the flakes flat, we flood the vial with UV light to cure the plastic into a solid block. The temporary transient magnetic alignment is now permanently captured and frozen inside a solid matrix. What we are left with is a solidified puck of UV resin packed with perfectly aligned graphene. Because of the precise internal structure, the object is highly anisotropic. Tilting it against the light, it shifts instantly from an opaque black wall to completely transparent, depending entirely on the viewing angle. We took the unique thermal, electrical, and optical properties of single-atom carbon and mapped them successfully onto a solid, macroscopic object. This exact technique is currently paving the way for advanced heat sinks that push thermal energy in one specific direction, ultra-strong lightweight composites, and entirely new types of optical displays. Mastering the magnetic alignment of two-dimensional materials provides the essential bridge necessary to take nanotechnology out of the laboratory and scale it for real-world engineering.